Hi everyone, welcome to our Math 70 lecture on section 1.1. We're going to talk through a couple concepts today and then do a whole bunch of practice problems. So, first of all, in this class, we spend a lot of time talking about equations. So let's define, let's have a working definition of equation. An equation is a mathematical expression. Expression is just how we call sentences in mathematics. It's a mathematical expression that includes an equals sign. So something like x equals 5 would be a mathematical expression that involves an equal sign. So this is an equation. This equation right here tells us that the unknown variable is equal to 5. Unknown variables in mathematics are usually represented by letters. The most common letter is X. Y is a pretty common letter. Z is a pretty common letter. I write my Z's with a dash here to tell that it's not a 2. And T is pretty common because T often represents time, but we can use any letter. We could use A or B or C, Q, etc. So as you work through your homeworks, you're going to see a variety of different letters. I'll probably mostly stick with X when I'm working with an equation that has one unknown variable, one variable. So this is an example of an equation. Here's another one. It's a little more complicated. 2x plus 1 equals 19. If I were to say this in words, and I'm not going to write it all down because it's too long, I would say you have an unknown variable. If you multiply it by 2 and you add 1, you get 19. Here's another example. Let me write example here. Here's another example of an unknown, or of an equation. 3 equals 2. Right? It's a mathematical expression that involves an equal sign, but obviously this is a false statement. Just because we have an equation doesn't mean the equation has to be true. So some equations are always true. Some are never true. And some are true for specific values of the variable. So I'm going to give you examples of each of those. By the way, there's a trade-off between zooming in far enough that it's easy to see the text and capturing the whole page in a single window. And I've chosen to prioritize being able to read the text easily. So I'm going to have to pause each time and change and move my page. So equations that are always true are called identities. Identities. An example of that would be 3 equals 3. 3 is always equal to 3. Another example of that would be 2x equals 2x. Because no matter what number x is 2x will always be 2x. Equations that are never true or equations that are false are called contradictions. As an example, 3 equals 2. That's false. It's a contradiction. Let me see if I can think of another contradiction. A very common contradiction would be something like 0 equals 5. Contradictions with variables. Let's think. Let me show you one. An example that involves a variable might look something like q plus 1 equals q plus 3. Well, no matter what number q is, 1 more than q cannot equal 3 more than q. We have identities, equations that are always true, whether it's because it's just a number equaling itself or a variable expression equaling a variable expression. Equations that are false, that are never true, like different numbers can't be equal to each other. If I have any number and I add 1, it cannot be the same as that same number adding 3. And then equations that are true for certain values of the variable. And in fact, we can have more than one variable. So I'm going to write variables are called conditional equations. The simplest conditional equation might be something like x equals 5. This is true when x is 5, because then it would be 5 is 5. And false for any other value of x. If I put 4 in for x, it wouldn't be true. If I put 90 in for x, it wouldn't be true. Often if we get down to x equals 5, we don't usually think of this as an equation. We think of this as a solution. X equals 5 is often called a solution because it tells you the value of x that makes some conditional equation true. For example, if I have 2x plus 1 equals 11, this is conditional because certain values of x will make it true and other values will make it false. If I put 100 in for x, 200 plus 1 is definitely not 11. But if I put 5 in for x, 2 times 5 is 10, plus 1 is 11. That's true. So this is also true when x equals 5, and false for any other value. These two statements are mathematically equivalent. 2x plus 1 has the same solutions as x equals 5. But a lot of algebra is taking an equation that looks more complicated and finding out the solution, finding the x value that makes it true. So let's quickly look at solving. I'm going to drop the word conditional very soon because almost all equations we work with in mathematics end up being conditional, so we usually just call them equations. So solving conditional equations means finding the values of the variable that make the equation true. Let's look at our example. 2x plus 1 equals 11. This is in symbolic form. Remember my four representations. We have symbols, verbal or words, numbers, often tables, and pictures, which will usually be graphs, and we can connect them all. Right, so this is a symbolic version of that equation. If I want to find out what x values make this true, we often solve this symbolically by saying if 2x plus 1 equals 11, then that should mean that 2x should be 1 less than 11. I can subtract 1 from both sides, and I get 2x equals 10. And if 2x equals 10, then half of that, 10, should equal x, or I can divide 2x by 2, and I see x should be 10 divided by 2, which is 5. So this would be considered the solution to the equation. And that's why I said these are usually considered solutions, because they're super simple. Let's do another example. Let's do x divided by 3 minus 4 equals 2. I could approach this the same way. I could say, well, if x divided by 3 minus 4 equals 2, I could add 4 to each side. But I just want to practice our flexibility a little bit. And I want to say, let's try to solve this using a number representation. I'm just going to put in different values for x and see if that can help me get closer to the answer. So if I put, what's a good number to start with? I like the number 0. That's always good to start. I would have 0 divided by 3 minus 4. Well, 0 divided by 3 is 0. That's 0 minus 4, which is equal to negative 4. This is not 2, and so x equals 0 is not a solution. I could try x equals 1. That's going to be 1/3 minus 4, and I can tell right away that's not going to be the number 2. So, in fact, it probably wouldn't help to put any number in unless it's divisible by 3. So let's try 3. That's 3 divided by 3 minus 4, which is 1 minus 4, which is negative 3. Still not 2, but it's getting closer. So let me try a different multiple of 3. Let me try 6. 6 divided by 3 minus 4, that's 2 minus 4, that's negative 2. No, still not 2. If you're thinking, why would I ever do it this way? I might not do it this way for a relatively simple equation where there's only a little bit of work to do. But there are some complicated equations out there, and sometimes switching it to a numerical representation will help. I've noticed as I increase my x, I'm getting closer to my answer. So I'm going to increase my x some more. I'm going to go all the way up to 15. 15 divided by 3 is 5, minus 4 is 1. Oh, I'm really close now. So I'll go one more multiple of 3. I'll go up to 18. 18 divided by 3 minus 4 is 6 minus 4, which is 2. Aha, I found it. X equals 18 is my solution. Why am I telling you this? Because you may find as you're working on these equations and solving these equations, you might be getting stuck with the algebra. You can always switch over and try using a numeric representation to help you. And in fact, there are also ways to solve it using a graphical representation, and we'll come back to that. So anyway, here's another example. And we're going to do more practice with this later, but just to show you the steps, I would add 4 to both sides. I would have x over 3 should equal 6, because 2 plus 4 is 6. And then I'd multiply both sides by 3. That cancels there, and I get 3 times 6, which is 18, and in fact, that is the same answer. All right, so I've showed you there are 3 broad types of equations. There are the ones that are always true, which are identities, the ones that are false, which are contradictions, and the ones that are true for certain values, which are conditional equations. And those are the ones that we're mostly going to be working with. And then I showed you 2 ways to solve a conditional equation. One is by doing the algebra, and the other is by converting it to numbers. You could think of it as guess and check. That's a great algebraic, a great mathematical strategy that I encourage you to use when you need to. How do you tell if an equation is always true, identity, always false, contradiction, or true for only certain types of values, conditional? And the way you do it is basically by trying to solve. By trying to solve the equation. If you can solve the equation for only a certain number of values, it's conditional. If you try to solve it and you get something that makes no sense mathematically, it's contradiction. And if you get something where it looks like, well, that's going to be true no matter what the value of my variable is, it'll be an identity. So I'm going to show you an example. Is minus 2x plus 8 equals 4x minus 16 an identity, a contradiction, or is it conditional? Now, just like before, you could actually try some numbers to get a sense. If I put 0 into here for x, I would have is 8 equal to negative 16. Well, no, that's not true. So it's not true for all my x values. But if I put, I don't know, other x values, it might work. So let's solve this one algebraically. In general, to solve an equation, you want to get all the variables on one side. That's your first step. So I have a minus 2x here and a 4x here. I'm going to get them all on one side by subtracting 4x from both sides. I'm going to get minus 6x plus 8 equals negative 16. And then we want to get all the numbers without variables on the other. Get all the numbers on the other side. So I'm going to subtract 8 from both sides, and I get minus 6x equals negative 16 minus 8 is negative 24. And then I'm going to isolate x, in this case, by dividing. I'll divide both sides by the minus 6. That will cancel and give me x equals 4. So I found one solution, which means it's not a contradiction because there was a solution, but it didn't give me something that looked like x equals x or 2 equals 2. So it's not true for all x's. So this one is conditional. All right, let's do another one. Let's look at 3x plus 5 equals 3x plus 9. And again, to figure out if that's conditional, a contradiction, or an identity, the easiest thing to do is to just try to solve it. Let's get all the x's on one side. And I'll do that by subtracting 3x from both sides. The 3x and the minus 3x cancel, and it gives me 5 equals 9. Well, this is false. doesn't matter what x value I started with, I'm going to end up with a 5 equaling a 9. That's false, so this is a contradiction, an equation that is always false. Let's look at another one. Let's look at 2x plus 7 equals, sometimes I have to work a little hard to make it happen. X plus 7 plus x. Let's get all the x's on one side. To do that, I'm going to subtract that x and also that x. So I'm subtracting two x's, and I end up with 7 equals 7. This is always true, so it's an identity. You may be able to look an equation and say, oh yeah, I can tell just from that, doesn't matter what x is, it's always going to be true. Or just from that, doesn't matter what x is, it's always going to be false. But I can tell you that when I wrote this one, I was trying to do an identity, and I was pretty clear that it's not always true. So it's worth going through the steps to figuring out whether you get a solution where there is one or two or three, but a limited number of solutions, or where you have no solutions because it's always false, or it's always true because it's an identity. All right, the rest of section 1.1 is just going through those steps to solve equations, which I've already done a couple of. I'll do a few more just to give you a little bit of a reminder about fractions and decimals. So let's solve 3.2x minus 1.701 equals 5.032. We're still going to use the same steps. We're going to get the x terms by themselves. So let's add 1.07 to both sides. As a reminder, when adding decimals, you add it like you would any multi-digit number. 2 plus 1 is 3. 3 plus 7 is 10. So I do a 0 here and I carry the 1. And then I have a 1 plus 0 plus 0, which gives me a 1. The decimal stays right there, and 5 plus 1 is 6. So decimal addition works the same as whole number addition, and a decimal will just float down. And so now I have 3.2x equals 6.103. So to isolate x, I'm going to divide both sides by 3.2. And this is not math that I'm ever going to do in my head. Once it switches to decimals, I switch to a calculator. So I'm going to open up Desmos because it has a built-in calculator function. I'm going to switch my screen sharing. This is what Desmos looks like when you land on the home page. And over here in the left, I can just use it like a calculator. So using my number pad on my computer, I'm going to put 6.103, and then I use a division sign, and it automatically creates the vertical division, and then put the 3.2, and there's the answer, 1.9071875. So I'll switch back to the notepad. 1.9071875. And I've solved it. This is a conditional equation because I found exactly one x value. Okay, I'll show you one more with fractions. So let's solve negative 2/7 x plus 3/5 equals 4/15. I just made this one up, but let's hope it goes well. So first we want to isolate the x, so we're going to subtract 3/5 on both sides. And when you subtract fractions, they have to have the same denominator. So let's do a little work here over on the right, just as a reminder. 4 divided by 15 minus 3/5. I don't just subtract the top and subtract the bottom. I have to make sure they have the same denominator. And to do that, we want to find a number that both of these denominators can divide into. And I picked a fairly easy number because 15 is 3 times 5. So 3/5 is the same as 9/15. So instead of doing 4/15 minus 3/5, I'm going to do 4/15 minus 9/15, which is negative 9 which is 4 minus 9, all divided by 15. And 4 minus 9, all divided by 15, equals negative 5/15. And actually that turns into negative 1/3. Didn't know that when I wrote the problem, but that's what it turns into. Now, if this was hard to follow, that's okay. It may have been a while since you've done fraction arithmetic, but it is definitely something to catch up on. So if you have access to previous notes from a previous class, or if you search on YouTube for a video, something like fraction arithmetic, you can probably get a refresher or a primer from that. And you can also always send me an email or visit my my Zoom office hours. So let's get back to what we were doing. I'm going to start the problem again just because I did a lot of side work. So we're going to solve minus 2/7 x plus 3/5 equals 4/15. I'm going to subtract 3/5 from both sides, and that's going to give me minus 2/7 x. And on the right side, I found out that 4/15 minus 3/5 is negative 1/3. So that's going to equal negative 1/3 here. And now I'm going to isolate the x. We can think of it in two ways. We can think of it as dividing by negative 2/7. But here we're going to use what's called the reciprocal. The reciprocal of a fraction is the fraction flipped upside down. So the reciprocal of negative 2/7 is negative 7/2. And so we're going to multiply both sides by negative 7/2. And now if you look, you see this 7 and that 7 cancel, and this 2 and that 2 cancel, and the minuses also cancel. And so that gives me just the x on the left side that I was looking for. And when you do multiplication, fraction multiplication, this time you do multiply across. So I'll take it a little more slowly this time. Minus 1 times minus 7. Sorry, that's a minus 1 times minus 7 on the top, and 3 times 2 on the bottom. Minus 1 times minus 7 is positive 7. 3 times 2 is 6. And I have solved my equation. X equals 7/6 is the number that makes my equation true. So again, if you want a refresher on fraction arithmetic, I would recommend just doing a search for that as a starting point. And then if you want more support, send me an email or schedule a time to meet with me in office hours, and we'll do more examples. So that ends our section 1.1 video. You have a couple more to watch this week. There's a lot of content in this class, so watch videos early, try to get ahead at the beginning of the week, so you don't have to do catch up at the end. I'll see you for our next video.